In this video, we're going to look at an example of gravitational potential energy using the movie Armageddon. The Armageddon movie was released in 1998. It was a very good sci-fi movie, in my opinion. In fact, I loved it when I watched it, even though, when I watch movies, sci-fi movies, which I loved, I really had to turn my sense off as a physicist. Otherwise, sometimes I really got bogged down with the physical reality of the plots in the movie, and sometimes it's ridiculous. This one, even though the numbers didn't quite up in terms of physics, I really liked the plot. I really liked the characters, and it was a good movie. Okay, but what I want to do today is to talk about the physical feasibility of the plan in that plot. So here's the synopsis of the movie. After New York City is damaged by hundreds of small meteorites, NASA discovered that an asteroid the size of Texas is on a collision course with the Earth. So, of course, it's up to the Americans to save the human beings once again. At least what the movie says. So and it was going to be just a month before the asteroid hit the Earth. So what they decided to do was to send a crew to fly over to that asteroid, and then they want to drill a hole all the way to the center of the asteroid, and they would put a nuclear bomb at the center and detonate it. Okay, the plan was to shatter this asteroid into small pieces so they won't hurt the Earth. That was the plan. That was beautifully executed in that movie by Bruce Willis. Again, it was a really fantastic movie, but do the signs hold up? Well, let's see here. If this is not the picture you want to see, let's see. How do we deal with that? So here, let's say we have an asteroid, okay, the size of Texas, and then we drill a hole. Forget about how hard it is to drill a hole. That's not the top point of this lecture here. I just want to know, from energy point of view, you drill a hole, okay, drill a hole to the center, and that's where you place a bomb, and then you detonate the bomb. So you shatter this into pieces, okay, into many pieces. Question is, how much energy would it take to make that happen? Okay, I want to know the amount of energy it takes to really shatter this into many pieces. Okay, so we shatter it into many pieces. Let's see how much energy it takes. Let's do an estimation. Okay, now the gravitational potential energy of two pieces of matter of mass m1 and m2, a distance all from each other, is a negative number if you treat the 0 point of the potential energy at infinity. Okay, and that negative number, the expression is negative g m1 m2 over r. That's what we got from the last lecture. Now what we have here is a whole bunch of matter lumped together into something the size of Texas. Okay, overall the potential energy has got to be negative, and when you shatter them into infinite number of pieces, and they can fly to infinity, then clearly the potential energy reduces to 0. Okay, so how much energy is needed to make that happen? You have to lift the negative potential energy all the way to 0 to make that happen, and the potential energy of this meteorite, of this asteroid, certainly depends on the shape and size of the mass. But let's say the roughly the size of this thing is r, and then the mass is m. Then roughly speaking, we're talking about order of magnitude g m squared over r being the size of this asteroid. Okay, so it's negative, and in order to lift this negative potential energy to 0, you have to give it enough energy So the energy released by the nuclear bomb has to be of this order of magnitude, delta E. Is of the order of G times the mass squared over R. Now, this is only an order of magnitude estimation. I mean, the actual expression of the energy depends on the shape and size, so you expect a prefactor in front of it, but that doesn't change the order of magnitude, at least not by much. So let's estimate the order of magnitude. Okay, now we know the size is about the same as the size of Texas, and the mass is density times volume. Okay, the volume we can approximate it as r to the power 3. I mean, there's, depending on the shape, there's a factor like pi or whatever. But again, I'm only looking at order of magnitude. So you can write m as roughly rho times r to the power 3. Okay, so this gives us delta E as G and then rho squared r to the power 5. Okay, because it will be rho squared r to the power 6 divided by 1 power of r. So you get this expression here. Again, forget about the prefactor because we're only estimating the order of magnitude of the energy it takes to break it into many, many small pieces. All right, now we know what G is, right? What is the density of the asteroid? Well, we don't know, but let's, in that movie, it looks pretty rocky. So let's assume it's roughly the same as the density of rocks on Earth. So we have rho is roughly 5,500 kilograms per meter cubed. That is also the mean density of the Earth. And R, the size of Texas. Okay, if you Google the size of Texas, you find it's about 800 miles or so. So I would say it's about 1,200 kilometers. I mean, it's not a perfect square, but that's roughly the size. Okay, so plug these numbers in. So you're looking at 6.67 times 10 to the negative 11 in SI unit. You have to convert everything to prime units, kilograms, meters, seconds. Okay, so this is 5.5 times 10 to the 3 in prime SI unit. Square that, and then r to the power 5. R is 1.2 times 10 to the 6 meters, and you raise to the power 5. Okay, now you do the algebra, you find the answer to be, of course, it's a big number, 5 times 10 to the 27 joules. Okay, it will take 5 times 10 to 27 joules to break everything apart. That's a lot of energy, but can a nuclear bomb do the job? A nuclear bomb releases a lot of energy, right? And even within nuclear bomb families, there are big ones and small ones. Let's suppose we take the biggest nuclear bomb ever made, ever detonated, and place it at the center of that asteroid. Will that do the job? Well, what was the largest man-made explosion, human-made explosion in the history of humankind? Well, that honor, or dubious honor, would belong to what's called Tsar Bomba. It was a hydrogen bomb detonated by the former Soviet Union in the year 1961. Okay, this thing was humongous, right? It was equivalent to 50 megatons of TNT, 50 million tons of TNT. And we compare that with the atomic bomb that they dropped on Hiroshima, that was only 20,000 tons. This was 50 million tons of TNT. And you convert that to joules, and that's roughly 200 PJP is 10 to the positive 15. Okay, so this is, you're looking at 2 times 10 to the 17 joules. Now that's a lot of energy released in a single blast. And this was the picture taken by the pilot of the bomber that actually dropped this bomb over the sky of Siberia. This was the fireball that was that was visible as a result of the explosion, and it's got a diameter about 5 miles. A fireball, diameter about 5 miles. That's a lot. And this bomb was so powerful that it shattered. It shattered glasses 1,000 miles away. It was felt in Paris. Okay, remember, this was in Siberia, deep inside Russia. So that's how powerful that bomb was. Okay, fortunately, it was not used in real combat. It was just, a show of force, really, to demonstrate how powerful, the Russian atomic bombs were. It was actually a hydrogen bomb. Okay, so it was 2 times 10 to the 17 joules. But if you put a bomb like this at the center of that asteroid, would that be enough to shatter the asteroid? Well, the energy it would take to do that, as we calculated, was 5 times 10 to the 27 joules. Okay, 27 joules. And here, each bomb, Zabomba would release 2 times 10 to the 17 joules. So how many bombs, how many Zambombas would it take to do that job? Well, N would be equal to 5 times 10 to the 27 divided by 2 times 10 to the 17. And the answer is just ridiculous. I mean, this is 2.5 times 10 to the 10. It will take 25 billion such bombs to make that happen. Wow. What does that tell us? It's just not possible. A single bomb is not even remotely close. As a matter of fact, you put all the nuclear weapons of the entire world, okay? All the current nuclear bombs in the entire world's nuclear stockpile, and put it in at the center of that asteroid. That still wouldn't be even remotely close to do the job. No, it's just not possible. Okay. Some would say, but wait a second, you don't need to shatter everything into small pieces, right? What if you just break into 2 pieces? So one flies to the left, one flies to the right, and hopefully they will both avoid hitting the Earth. That sounds like a better plan, right? That sounds like something more feasible. But how much energy would it take to do that, you wonder? Well, let's see here. You have to basically, initially you have to lift this much negative energy, right? Now the final product, the energy is not 0 anymore. It's still negative. It's actually made of 2 pieces, each piece with half the mass and the smaller radius, right? And all you have to do is come up with the difference. So E initial, so a new plan. Break it into 2 pieces. Only into 2 pieces, not infinite number of pieces. 2 large pieces. Okay, so E initial is negative G mm over R. I shouldn't be using the equal sign because it's not accurate. Okay, so I'm just like this. What about E final? E final was 0 if you break everything into infinite small pieces, but now it's not quite 0. Rather, it's still a negative number. You got 2 pieces, right? You got 2 pieces. Each piece has a negative energy. How much is that? Actually, this is m squared. I'm sorry, m squared. Right? So I'm going to put m squared here. Okay, so now each piece has half the mass times g, and you square that, and you divide it by a smaller radius, right? A smaller radius, how much smaller? If it's half the volume, does it also have half the radius? Of course not. That's ridiculous, right? If you have initial volume, initial radius is r, the new radius we call it r prime. Then the volume is proportional r to the power 3. So therefore, if you raise to the power 3, that will be v over v prime. V prime is half of the original v. So this is 2, and you can calculate r prime. So r prime is roughly 0.8 times r. Okay, so it's not half the size, it's about 0.8 size. So don't forget there's a negative sign. So this is the final energy. Okay, And look at how close it is to the initial energy. You have a factor of 2. So this is negative 2 divided by 4, and then divided by 0.8 times, gm squared over r. So you compare with the original expression, you have this extra factor here. Okay, you have this extra factor here. Here's the extra factor. And this extra factor is not that far from 1. It is about 0.6. Okay, so you're looking at roughly negative 0.6 of the initial energy. So good news is that you don't have to lift initial energy all the way to 0. You have to lift initial energy to about 0.6 of its initial value, which is still negative. And therefore, delta E, this time delta E, is E final minus E initial. But E final is 0.6 times E. So you're looking at 0.6 initial minus E initial. So therefore, it is 0.6 E initial minus E initial. This is negative 0.4 E initial. Okay, so E initial is negative, so overall delta E is still positive. We know what E initial is in terms of magnitude. This thing is, as you know, 5 times 10 to the 27. Okay, so now you don't need quite as much, you need 40% of that much. Okay, so your job is easier because you only need 40% of the energy that you would have to expend. But 40% is still a lot. 40% of 2.5 of 5 times 10 to the 27. So you're looking at 2 times 10 to the 27 joules. So therefore, the good news is you don't need as many Tsar bombers anymore. You will not need 25 billion such bombs. You would only need about 10 billion of such bombs. Okay, but that's still ridiculous, right? So therefore, the scheme will not work. Okay, forget about something the size of Texas. If you have something with a cross size of a few miles, that will be really something that we cannot do with today's technology, according to that scheme. So you got something that size, something 100 miles or more, hurtling towards the Earth. What can we do with today's technology? Well, unfortunately, the answer is nothing. We don't know how to avert a disaster if something like that happens. Okay, and something that size or even bigger, did it ever hit the Earth before? Yes. And will it hit the Earth again in the future? Yes. Hopefully. There's a long time interval between two events like that. I mean, there's a common accepted theory how dinosaurs got extinct. It was because of a large asteroid hitting the Earth. So events like that have happened before, and they will happen in the future. It's a matter of how much time we have till that happens, and whether or not by that time humans, if we still walk on this planet, will have enough technology to intervene. And regardless of what happens, it looks like based on the energy that we can command, even with nuclear energy, breaking it into pieces is not something feasible. What we might think of maybe is to strap a powerful engine on this thing and try to divert its course. So you don't break it to pieces, you just nudge it to the side. At least from energy point of view, that seems to be more feasible. But still, we don't have the technology as of today. Okay, so that is our discussion of the physics of this movie. So it looks like from energy point of view, the scheme will not work. All right, so we have one more lecture, also has to do with science fiction, and we're going to talk a little bit about the so-called three-body problem. It's a well-known science fiction novel. We're going to talk about what three-body problem really means in real-world physics. And we're also going to talk about the concept of Lagrange points. So that will be in the next and final lecture of this chapter.